sequence. So three-phase voltage is divided into the symmetrical or this phase sequence. Now the phase sequence is defined as the sequence in which the three-phase voltage reach their maximum positives. So it is not fixed that they are almost divided into the 120 degree or any 240 degree. They can be achieved their positives at any instant. So the phase sequences can be reversed by interchanging any two phases. So if you are changing your voltages applied to any two phases, then it may be changed to the peak value of that particular phases voltages between the voltages. This is one of the video for polyphase circuit. This gives you the brief indicate the principle of three-phase circuit.
We will begin our examination of three-phase electricity by first looking at one complete cycle of AC current. Notice that one cycle of electricity consists of 360 degrees, which can be divided into two 180-degree divisions called alternations. The first half cycle is the positive alternation, and the second half cycle is the negative alternation. As you can see from this simple illustration, the current flows in one direction for one alternation, and then flows in the opposite direction for the second alternation. Also notice that the voltage potential constantly changed values as the sine wave went from 0 to maximum positive peak and back to 0, then from 0 to maximum negative peak and back to 0 again to complete one cycle. Here you see the AC sine wave being illustrated with a bicycle pedal used to illustrate the 360-degree cycle. When the front pedal is between 0 and 180 degrees, the pedal is in its positive power portion of the 360-degree cycle. When the rear pedal, behind the sprocket, reaches the 0-degree point, it produces the negative power portion of the 360-degree cycle. The power portion of the 360-degree cycle be considered as that part of the cycle which causes work to be done. On the AC sine wave, the power portion of the alternation is that part which is either above or below the 0-volt reference line. On the bicycle pedal illustration, the power portion is that part of the complete cycle in which one of the pedals is being pushed down. As you can see, when one pedal is being pushed down, the other pedal is being returned to the 0-degree point. The return pedal stroke is not supplying power during its portion of the cycle. Now suppose that we use three of these waveforms working together to supply electrical energy into a circuit. Notice, in this illustration, we are showing three identical waveforms. They all have the same amplitude, frequency, and phase. In order to make these three identical AC sine waves work together in their most efficient manner, we must separate them by equal amounts. Since a complete AC cycle consists of 360 degrees, and we need an equal separation between the three AC signals, we will need to separate them 120 degrees from one another. Notice that phase A starts at the 0-degree point and completes its cycle at 360 degrees. Now notice that phase B starts 120 degrees from the phase A sine wave and completes its cycle at 480 degrees. Phase C, on the other hand, starts 240 degrees from phase A and completes its cycle 600 degrees from the start of phase A. To illustrate the effect of three-phase electricity, we will use three sets of bicycle pedals. Each pedal is set 120 degrees from the other two pedals. As you can see, the front pedal of phase A starts at 0 degrees. The front pedal of phase B starts at 120 degrees, and the front pedal of phase C starts at 240 degrees. Now let's compare these pedals to a three-phase sine wave. As you can see, the sine wave for phase A starts at the 0 reference line and then increases to its positive peak potential. When compared to the start of phase A, phase B is actually 120 degrees into its cycle. And when compared to the start of phase A, phase C is already 240 degrees into its cycle. Here you see all three phases operating simultaneously. Notice that at any given point in the three-phase cycle, At least two of the phases will be working together to provide power into an electrical device. Since the phases are all separated by a 120-degree phase shift, the return current from one leg will feed back through one or both of the other legs. With all three phases operating, it is much easier to cause the armature of a large AC motor to rotate, due to the fact that three 60-cycle AC currents are working together to cause the rotation. Another major benefit of the three-phase system is that it is much easier to rectify into direct current. As you can see, three-phase electricity is not that difficult to understand. However, you should know how it works because it is used extensively throughout the manufacturing industry due to its ability to produce more usable power than can be achieved through the use of single-phase electricity. Many of the larger AC and DC servo motors use three-phase electricity as the incoming power source. Also, many of the larger AC motors used in servo systems operate from a variable frequency AC power source. You will learn more about this later. Now let's examine the operation of the AC motor.
Some of the terms which are using in the three-phase circuit. So just we go through the brief overview of that terms. Like a phase. What is the phase? It describes by the one element or any device in a load, line or source that is simply a branch of the circuit, which defines the branch of circuit. So for that, in our circuit, R1 and suppose R2, so this is called one device or one element. So R1 and R2, this indicate one phase. The next one, that is a line, which refers to the transmission line or the wires that connect the source to the load. It may be modeled as a small impedance or even by just a connecting lines. Like R phase, same here, the central point is a N, the second phase and the three phase. So this is called the lines which are connected with either the source or with the load side, output side. The third term that is mostly used, that is a neutral, the fourth wire in the three-phase system. That's it's a where to phase of the Y star connection, or you can also use with the delta connection, but generally it is connected with the consider from the star connection, or it's a Y connection. So here in our figure, that N is a neutral point where all the three phases are connected with each other. The second term, that is the phase voltages and the phase current. The phase voltage and the current across the phases and through a single branch of the circuit. So not that this definition depends on whether the connection of that is a Y connection or delta. You have to remember this one. If you are talking about the Y connection, then these are the definition maybe slightly differ than the other one. So here, if this is the phase R1 and R2, so this is phase R, this is Y and this is phi. So across that R1 and R2, whatever the current passing through it, that is known as a phase current, and due to that current and the resistance of that coil, the voltage is generated across this is called the ER. So this is called phase current and this is called phase voltage and this is called phase current. The next one, that is a line current. The current flowing in each line, this is called the line current. Like that, if this is a phase R, then the current passing from here is called IR, line current. Okay. The phase Y, so the current passing from the source to phase Y, that is called something IB. So IB is related to the line current of your phase Y, and the same here, if the from the source side the current flowing is IC, the current is IC, then it is IC is flowing from the phase B. So these are the three line current, IA, IB and IC. IA is related to R line, Y and B line. So these are the line, and from the lines, the whatever the currents are passing, these are the currents known as the line current, and the current flowing from the phase are known as the phase current. Now the line voltage. The voltages between any two of the lines are known as the line voltage. Again, if we are taking that, three lines, this is neutral, line 1 for R, Y and suppose B, line 2 and suppose line 3. So any two lines, the whatever the voltage is generated across the two line are known as the line voltage. So here we can find out the voltages between R and Y. So these are the voltage known as EYR or RY. So E1 is the line voltage between Y phase and R phase. Same here for the line 2 and 3, this is E2 between Y phase and B phase, and the third one is from the R and B, this is E3 between R and B. So these are the currents, or these are the voltages known as the line voltages between two lines. In the single phase system, only the two wires are required to transmit the power to the load. This is the example of single phase system. This is the input section, and here you are something making one circuit, and here something load, and finally from the RL you are getting some output. So the two lines are required in a single phase circuit. This is called single phase circuit. This is now the supply connection of this is the figure which is exactly how the three phase voltages are generated in a polyphase circuit. You can see that the R1 and R2, Y1 and Y2, B1 and B2, these are the phase, three phase, and all the phases are connected with the load. If we make such kind of connection, then what happens? You can see that the three loads are required to connect with the each and every phase. Then what happens? Say as shown in a figure, if all the 6 terminals R1, R2, Y1, Y2 and B1, B2, these are the 6 terminals of the three phase system, are used independently to transmit the power to the load, so then it requires almost the 6 wires. So this method of the transmitting power is very costly. Whenever you are increasing the number of wires, the number of terminals, then the requirement of the number of cost of that transmitting the power which goes to very high. So we have to remove that, we have to overcome that method. So instead of that, what we prefer? So to reduce, to overcome the overall cost of the three phase system, the three phase system must be connected in particular fashion. So instead of that fashion, R1 R2 connected with the load, Y1 Y2 connected with the load, and B1 B2 connected with the load, instead of that fashion, we just put out the two different methods which are mainly preferred in a polyphase 3-phase circuit. These are known as a star connection and the delta connection. So all the 3-phase circuit, either it can be used for the transmitter section or the receiver section, they are connected either like a star fashion or the delta fashion. This is the overview of the star connection. This is also known as a Y connection. See, the 3 phases known as A, B and C, and the A phase is your reference phase. So you can see that the vector, the phase difference is the 0, and B is your lagging phase, that is a phase number 2, that is 120 degree lagging with the phase A, and the phase C, that is 240 degree lagging with the phase A, and we can say that in the manner of the leading, then C is the lead by the B phase with a 120 degree. So this is the connection for Y. Now in a Y connection, this is the connection is formed by the connecting starting or the ending terminals of each phase together. You have to connect the starting point and the ending point of each and every phase. This is common point which is known as the neutral. So each and every the phase starting point is connected with the source side, and the other terminal of each and every phase is connected with they are connected with the same point, and this point is known as a neutral point. See here, the starting point, this is suppose starting point, this is suppose the starting point for phase R, this is starting point for phase Y, and this is starting point phase B. So these are connected with the source side. And what about the other phase, other terminal of each and every respected phase are connected with each other and given to the terminal neutral. Now this is the connection of delta. You can see that the A, B and C, again these are the 3 phases. The voltages between V, A and B phase are 0, B and C, that is 120 degree, because the B phase is the lead by the lagging by the A, that is 120 degree. So VBC equals to VAB equals to minus 120, and between the voltages C and A or A and C, that is 240 degree lagging. This is the delta connection. Now in the delta connection, which is how it can be formed, it can be formed by connecting the end terminal of one winding to the starting terminal of other winding, such like that. Suppose the phase